So, why are we? Why am I? Why do I want to give this talk? This here is the goal. First, some acknowledgements that the system I'm going to show you, the digital twin we have built, is thanks to the efforts of these are the main stakeholders. And then we have a larger section where we work at the Electrical and Computer Engineering Department of Aarhus University. This is just our small part of the department that's focusing on software systems. And so we have a fairly large and international team. The reason we built this system is because it's currently difficult to establish exactly what a digital twin is, right? And to establish how do you connect the definition of the digital twin with the promises made by having it. And we work a lot with companies. So much of our research is in connection with the companies, inspired by the company's problems, and often we have companies coming to us and asking, we want to build a digital twin because we have these expectations, and then we try and see, okay, how do you go about building a digital twin? How do you go from this definition of digital twin that's commonly used to the advantages? So the typical definition is, so what we do is we built a small digital twin system, and we started from the business case because we're talking to companies. They need to understand. They often they want to know where's the money, right? So we have a small example here of a company called TwinPay, and it's making the purpose of this company is to build a device that allows you to produce this food called tempeh. And this is inspired by this is a food that's produced in Indonesia. It's made from fermented soybeans. It is the tempeh product is rich in protein and nutrients and low in CO2 emissions. So it's one of the highest protein per CO2 emissions that you get. The recipe is here. This is traditionally done in Indonesia. I'm not going to show too many details here, but I want to convince you that we have built a system. In fact, I have it on my office in there in the corner, and I'll show you later. But we have produced tempeh. We have tasted it. No one died, and we have our digital twin of this system. I'll explain later what that digital twin is in detail. But our system, our incubator box is the physical twin. It is, it is really focused only at this stage of the recipe, where the rest is manual labor. We have to prepare. There's a small fungus we feed into the soybeans, and then the fungus will grow, consuming part of the soybeans, which is typically the part that we don't digest anyhow. So it's actually better. It increases the bioavailability of this, and then the product of this process is this dense paste that tastes a bit like mushrooms. It's very nutritious, but of course, then we slice it and deep fry it, and then by the time you're deep frying it, all the nutritious value is gone, but the taste is quite good. So that's how it looks like when you slice it, and this is how it looks like when you deep fry it. So our physical twin is this incubator box. It's a rather simple system, and it fulfills the basic requirement of tries to keep the temperature around 37.5 degrees. That's the optimal temperature for the fungus to develop, right? We're in Denmark, so this system can be implemented. Doesn't need any kind of air conditioning. It just really warms up the system. The room temperature is always colder than 37.5 degrees. So the system is a very simple one. The reason I say this is because our physical twin comes before the digital twin, and this reflects the typical situation we face with the companies that come to us, that they have a system in place in market, right? And they want to build a digital twin for it. So there are there are certain number of requirements that that are already fulfilled, and they want to increase the value of their system, of their digital twin enabled system, right? Using the digital twin, but there is a core value already present in the physical twin. So this distinguishes the digital twin from a traditional control system, right? If I were designing a control system for this incubator, I would uh, try to build a controller that fulfills this requirement. But I'm not building a digital twin that fulfills this requirement. I'm building a digital twin that's going to do more, that's going to increase value in other parts of my system that maybe were not originally intended to fulfill. So, for example, I wish to uh, enable visualization. So I wish to show the users that buy this incubator. Maybe I wish to sell it as a service to those users, the ability to visualize their incubation process in the past, right? Create value by adding nice graphics and lots of plots. That's a common requirement we see in digital twins. Um, Another requirement here could be save energy. So we know as part of making the template, the user will need to open the lid occasionally to check on the progress. And so um, nothing really bad happens if the user opens the lid and closes it right away. But if the user forgets the lid open, then we're wasting energy, right? So we may want a system that can intervene, reconfiguring the controller of the physical twin when the lid is open to save energy, right? Um, Another requirement could be we want to signal to the user that the tempe is ready, right? To try and can we infer the readiness level based on just temperature and heater data over time? Because that's what we have in our incubator. I didn't start with that, but we have two small temperature sensors inside the box. We have a temperature sensor outside the box, and we have a Raspberry Pi running a simple controller that keeps keeps the temperature there, right? And then we are building the digital twin after that. Um, Other requirements. These are a summary of the requirements we see when we collaborate with companies, right? Predictive maintenance, signal that maybe the fan is working not so well as from when the product was built, right? Detect when tempeh has gone wrong. It can happen. Measure temper quality. This is like a quantified version of this one, and then actually trying to figure out better control policies to improve the temper quality. Um, so these are examples, and you can see a parallel between this and what's happening in the manufacturing domain as well. So they're very similar. If you have a manufacturing cell, you have similar requirements. So where is the digital twin in all of this? Let's cross against the definition. We have a data flowing between the physical twin and the digital twin. A digital object, yes. Okay, we have data flowing, and we have time series database, for example, where we are keeping this data. A change made on this side, on the digital, will lead to a change to a digital object. And this is depends on the business case, and we typically do not. It's hard to say we have a digital twin because this. It will really depend on what are we tracking, right? We can't just mimic every change happening here directly here. So some changes are just not smart, right? So in this case, certainly, if we wish to reconfigure the controller on this side, we can propagate that change in here, but as a result of the lid being detected open. So this will depend on the requirement. We have to start from the business case when we do companies, when we work with the companies. And finally, yeah. So on one hand, changes are happening here. They are being detected here. So if we open the lid, we would like to detect. But again, it's about what are the changes worth tracking. Some changes are too expensive. For example, detecting a bad tempe batch may require tons of data about previous batches that we simply do not have at this stage. So we cannot detect that change, right? But detecting the lid is open is something that can be done with relative ease. So it will depend on what we wish to do. Um, This is our own example system, and you can see the temp at the beginning, you can see it in the middle of the process, and you can see it at the end. This is a successful case. And you can see the heater over here, the fan, and the temperature sensors are on the sides. We had an extra box of sensors. I'll explain why we had that later. We were testing a few things. You're welcome, very welcome to this. All of this is open source. So we've collaborated already with other academics when they build a digital twin system, and they've used this as a case study because we built a simulator of the system, so you can run basically this thing on your laptop without having a connection to the real system, and you can then play with your own digital twin. You can try and figure out how to optimize things. But we have, this is not a toy example. We meant it to be simple, but we have experience in our lab building systems that are, that are a bit more advanced, like robot manipulator tracking. So we have a small demonstration here. This is not just displaying the angles. You see the visualization here of the angles of each joint, but you also see a prediction of the currents being drawn by a model. So a fairly large model estimates how much current is being drawn by each joint, and then is plotting on top the actual current measured by the robot. What are we going with this? We can do predictive maintenance with this because if friction is increased on the joints, then the friction will not be increased on the model. And so we will at some point observe divergence between the predictions and the real system, and that will tell us that there is some problem at the joints, the corresponding joints. We have small agricultural robots. This is one built by the company AgroIntelli. They built this one, but obviously we can't have this in our lab to play with. So they built a smaller version of it for us to play with. And so here we've built some digital twins of. You can see here an example where we're using gazebo. And here the digital twin is intervening. Okay, it's a bit difficult to see. There's a lot going on, but the digital twin is intervening to stop the robot because an obstacle was detected at the map, and only the digital twin knows about the map. So the robot is a bit blind in this example. Yeah, we've also done a fun project where we have this little car that can run up to 80 kilometers per hour, and we have, in this case, a common filter. So we're collecting data about the system, and we're trying to detect what kind of floor is it driving in, so that we can configure the driving controller accordingly. Yeah, we have examples with organ preservation as well. So I'm not going to go over too many of this because I actually want to show you the meat, but yeah, we have multiple examples where we've built digital twins, and this system, this incubator system, is sort of summarize the challenge or summarizes how we've tackled these problems. Yeah, so the first requirement of keeping the temperature at 37 degrees is easily fulfilled by this is traditional. This to us this is control engineer, right? This is control problem. So we don't attempt at work with it on our digital twin, and we can discuss that later if you don't agree. That's totally fine. The visualization, our architecture of the digital twin for this incubator consists of two important components. One is the communication framework, which we are using a RabbitMQ server, and an InfluxDB, a time series database. Right. We try to make it as simple as possible so new researchers and so on can understand. And so these two components are critical for the good operation of this system. So you may argue, oh, we should use an SQL server to keep track of different configurations of components. I would agree. We should use a Kubernetes deployment to keep track of the running multiple services and redundancy and so on. I also agree with that, but we want something that people can clone and get started quickly. So we simplified as much as we could, because we also give tutorials to companies, and so it makes it easier. But essentially, this RabbitMQ server is available by the controller. So the controller uploads the data to the RabbitMQ server, and then within the RabbitMQ server, we can have a component that stores all the data into the time series database. And this could be a custom script. It could be what's the name of that technology? Telegraph. That's just bridging all the communication into the time series database, so you have a record of what happens in time, right? And then you have for the visualization, then you have another service, which again some other server running that can take the data in the time series database and build a web page with that data that then the users can access, right? So these three components are essential to the functioning of they form the basis of our digital twin, and then we have different servers that are implementing services, and they collaborate to implement the requirements of the system. There's a small demonstration of our dashboard for visualization. We used the InfluxDB platform to build the dashboard as well. We could have used Grafana or other platforms out there for visualization. You can see the heater signals on and off. The fan is always on, and you can see the temperature evolving. In this case, this is the average temperature between those two sensors. And there's some other signals here. I'll explain what those are later, because we're also visualizing other things. The saving energy requirement. So here, one way we went about it is to would build a model, and this is similar to how we solved other problems with other case studies. Part of it was building a digital model of the system, making sure the model is predictive, can predict how the system should behave, and then we use that model as a way to detect anomalies when the predictions don't match the real system behavior. Right, so that's essentially what these breaking down these requirements is doing. Why can we use a predictive model here? Because we see from the data that clearly there's a big difference between the system operating with a closed lid and the system operating with an open lid. So we see a big difference in how the temperature evolves over time. So if we build a good model of how the temperature should evolve over time with a closed lid, we should have our work cut out for us when we open the lid of the system. There's a few typos here, sorry about that. Okay, so this is to me, my experience, because we've built already multiple case studies, this is a step where we spend the most time. Right now, the toolings are in place for us to build the rest of the digital twin for the incubator, but building a good model of the system, of the dynamics of the system, is something that's difficult. And let's say we spend like 60-70% of the time in the whole effort of building the digital twin in this stage. Fortunately, the incubator is a simple system. It was selected because of that, because we have very simple equations describing its evolution over time. And importantly, these are actually really good in practice. So we can conduct experiments in practice, and you can compare the predictions or the equations with the real data, and you can see there's very good agreement. I'm not going to go into the details of the equations. I'm happy to discuss them later, but the experiments we conduct are simple. We fix a particular heater on and off signal. We run it through the real incubator. We collect the data with a closed lid. We run the same signal, and there's a room temperature signal as well. We run the same signal through the simulator with the same initial conditions, and we start with some guess of the parameters. And this typically leads to a bad simulation result that doesn't quite match. But then we can use this previous one and adjust the parameters a bit more, and we can keep adjusting until the simulation results for the period of our simulation are in good agreement with the data. And that's how we calibrate the parameters of our model. Because we can get a system of differential equations describing the behavior of the system, but it's got a bunch of parameters that we need to estimate their values for. And this is a whole field, like figuring out the right values for parameters, depending on a robot manipulator, for example, is hell. But in this incubator, it's very simple. It requires a few experiments and you're done. I could have used a neural network to achieve a similar behavior, so we can discuss it later if you're curious. But could have used it in a neural network if I didn't know any of the physics. But in this case, I know the physics, so it's easy. Once we have this model, we need to solve another problem, which is every time. So I cannot let's say my simulator, my monitoring service that will be checking if the lid is open will be running 24/7, right? So I can't just run a simulation in parallel with the physical twin and totally ignore the values coming from the physical twin. I need to somehow find ways to combine that data into into making my simulation more accurate, because my simulation will naturally diverge. It will drift because there are small errors that just accumulate in the simulator, and they at some point my simulation would look very different from my real physical twin if I always ignore the data. So I need to combine the data. And that I do using a Kalman filter. I'm not showing you the details in this part because this is a bit more involved. But remember, the simulator is just something that takes a room temperature and a heater signal and gives you a prediction of how the temperature evolves for the duration of the heater signal and room temperature. It's not something that takes into account how the real incubator is behaving. But a state estimator has that crucial difference that it is taking into account the real data into estimating the next temperature. And as a result, it can give you a far more reliable simulation that can run 24/7 without drifting, right? While at the same time, you can still use it for predicting um, momentary, quick prediction errors. And that's what we are using to predict the open lid. So I have a small example here. And you can see this slightly noisy signal is the real data. Um, and the output, so the blue line is on top of the purple line. You can barely see them together because they're just one on top of the other. And here we open the lid after a while. And you will see that there will start to be a difference. Here I zoomed in, and you'll start to see a difference between the purple and the blue line. So you see they're slightly different, but that's still normal. This is still totally fine. And then we will open the lid. Yeah, now the lid has been opened. And you can see the blue line continues going forward, whereas the purple line drops. And that's how we are using, you can see here. And that's the basis that we are using to detect that the lid has been open. It's when our prediction model give bad errors. And here you can see a full data set. You can also get online the data set for this experiment. So what's going on? We have our state estimator service, whose job is to just put in the time series database, for example, what should be the next value of the temperature after 3 seconds based on what it has seen so far. And then we have another component, another service, which then looks at all of this data and can give an answer. Is it open or not? And finally, we have another service, which by now it's trivial to implement, that then can react to any signals of the lid being open to, for example, shut down the controller or reconfigure the controller. And that's our, let's say, we have the basis of our digital twin that enables communication and recording of the data in the time series database. And then we have these services that can be added later. Once you understand better how things are working, they can be just added better. So I'm not going to go over the challenges because time is running out. I just want to move on to the next requirement, and I'll come back to the discussion of these previous architecture. In here, if we focus on why on trying to measure that the tempeh is ready, there is evidence. So research was published in the 60s, 70s, showing multiple experiments in the lab by a guy who really wanted to spend some time in Indonesia, but he was from New York, and he made a number of experiments, and he showed that on average the temperature of the tempeh follows this curve. So after about his results says that after 35 hours there is a temperature peak, and shortly after that the tempeh is ready, and this is 35 hours. Now tempeh is a biological system, so these batches are very different. For example, in our case, actually, after 18 hours, we observed that the tempeh was ready. So, sorry, after 24 hours, after 18 hours, we saw the peak. This peak happened about after 18 hours. So this is one batch in a controlled lab environment. You're more than welcome to build your own incubators and send us more data, because, and this is, by the way, one of the big advantages companies wish to have a digital twin, because in the case of this twin pay company, what it could do. Oh, sorry, I didn't quite explain the plot, but what you're seeing here is the temperature evolution, and this is a system. You can see that the control signal, the controller is using less energy. The heater is being turned off, turned on fewer times after 18 hours. And that's because the tempeh itself is generating heat. So there's an extra source of energy in the system, and that we can see it from the data. So it's possible to detect when is the tempeh ready. We just need a lot of data because this is a biological system. And here is where this is an example of real data set where in this case we could turn off the controller after a few hours. I don't remember how much time in this example what was. We could turn it off, and you could actually see it can still sustain itself after a while. There's so much energy being produced by this chemical process that the system can even sustain itself without any further turning on the heater after some time. And this is, of course, the Wi-Fi failed in this data set. So you see, this is a realistic data set with all the usual stuff you see. So why is the advantage of having a digital twin for the twin P company? Because they can have a lab where maybe they have 2 or 3 prototypes, and they can have very preliminary data to implement a few basic services to their customers. But thanks to the products that have been solved, and if they have agreements in place to collect the data from all the different products that have been solved, they can now collect massive amounts of data and actually build more and better services for the customers. Right, so this is the big advantage in establishing a digital twin for their system. So one of the challenges I've described so far, none of them is particularly new. Each of these things have their own research field, and so there's a lot of reuse. There's a lot of things we can reuse from there, but the fact that we now have an open architecture of services that have a certain API that can be used into developing subsequent services. This is one of the big things in digital twins from as we see. And now in the case of incubator, when you compare the way we architected the system with the service-oriented architecture, you see there's an almost exact match between the two. So we argue that for the digital twin of this incubator, a service-oriented architecture is quite good. We do not need more than that to get things working. And we would like to discuss more with you what the differences are and what things are we missing. So here, sometimes I just want to, in our view, a digital twin is often confused with a model, but hopefully I convince you that they are different. We use a model in our system, right? We've calibrated that model. We've estimated the parameters of that model that predict how the system behaves. We've built simulations of that model, and usually we frown when people say it's a high fidelity simulation. Usually, what is a high fidelity simulation of our process? Do we really need a computational fluid dynamics to describe the flow of heat inside the box? We built that, but it is of limited use except to optimize where to place the heater and the fan. Right? When we're designing the system, we may wish to build a high fidelity simulation of our incubator to ensure the temperature is uniform, for example. Beyond that, to do the monitoring in practice, we don't need that complexity. And it's also not a control system. I hope I convinced you of that early on. So one of the big challenges we have is the disciplines coming together. Is the fact that we we need to know about the physics, and we need to know how to combine the physics with state estimation, filtering, and then combine that in deploying that in a software, in a service-oriented architecture, and understanding well how the delays in the system affect the system. So these things coming together is a challenge we often see. We argue that propagating uncertainty is something that is very interesting. So uncertainty quantification has been researched a lot, but maybe it will some of these old techniques will have we reemerge because we are composing all these different services taking decisions that ultimately can affect the controller. So being able to quantify the uncertainty in each of these decisions and making sure that uncertainty as it is propagated is decreasing can be a very interesting, or better yet, understanding under which conditions does that uncertainty decrease as we compose it in other services before we can make a decision. That's interesting. I didn't mention, but we expect most of the times the physical twin is certified and commercialized, right? But the digital twin, if it gets added, is typically outside of the certification. So making sure the digital twin decisions will not break the certificate of the physical twin is something that's important. So formal methods and all the discipline is becomes very important. This is an example of safety. This is an example precisely where the digital twin, in this case, actually the physical twin can, without the aid of the digital twin, can become unsafe, right? So in this case, where it's the lid, if the user opens the lid, and this is an example we have reproduced in our physical system, if the user opens the lid for a long time, the controller will go into full power, which then makes the heater, as because it's a piece of metal, it's a resistance, to become very, very warm. And then when you close the lid, all that heat is only can flow in one direction, which is towards the tempe pouch, which then means it will heat up too much the tempe pouch, causing a spike in the temperature of the box, and thus affecting the quality of the tempe, because the fungus will tend to die off at higher temperatures, higher than 45 degrees, I think. So this is an example where if we're not careful about how we compose the different digital twin services, they may reconfigure the controller in the wrong way to go full power, for example, if the lid is open, or they may fail to intervene on time. So this is, ideally, we have an architecture of the digital twin that will validate the decisions as well, build confidence in decisions to be made before they are actually propagated into the physical twin. And this is there's a big overlap with the safety in self-adaptive systems, which is a community that has they have studied this problem, but the physics play an important role here. So this is where we currently have a project precisely looking at this part of safety regarding our adaptation loops. So we have a strong link with the MAPE-K architecture and self-adaptive systems. That's about it. Sorry, I went a bit over the 30 minutes, but I'm happy to discuss any questions you might have.